Hi everyone, welcome to the lecture series on advanced structural analysis. Influence line diagram for the specific topic of today's is the ILD for continuous beam end reaction for a end reaction. So let us look at a ILD for a end reaction, that means end support for a continuous beam. Let us say ABC, a two span continuous beam, and we can see I can have ILD for RA, can have ILD for RA, can have ILD for RB, ILD for RC, which is similar to ILD for RA. Then I can have ILD for movement at somewhere in between, at section somewhere, let us say some X section at any span, and shear at same section, and also movement at mid support. So these three plus these two, RA, RB, movement at X, shear at X, and movement at B. So these 5 types of ILDs you should learn. So now let us discuss ILD for RA. So I have taken this beam, span of AB is 5 meter, BC is 5 meter, and like to get ILD for reaction at A. So now what to do? Simply apply a unit reaction at A and see the deformed shape of the beam. See the deformed shape of beam, that will be directly the ILD. So this is very simple. If we understand, by applying unit reaction here, the beam goes something like this upward, and the deformed shape of this beam will be the ILD. Simple. So this is the ILD shape of the RA simply. So now it is only the matter of finding the ordinates. Finding the ordinates here and finding ordinate at a distance x, okay, at a distance x, and also trying to find ordinate here at this span at a distance of x from the support. Then dividing this by this and dividing this by this will give me the ILD ordinate for the RA. Very simple. So let us see how to solve this problem. So now what it do? So because I applied unit reaction 1, so let us find out the reaction RB and RC in this case. So for this beam, taking movement at, let us say, C, taking movement at C gives me here, taking movement at C here, so I have RA. Now again, see, I'm taking movement at the C and I'm going towards the right hand side. So while going to the right hand side, RHS clockwise are positive and anti-clockwise are negative. So 1 into this total distance how much 5 plus 5, 5 10, which is clockwise, so taken positive. So an RB, again this is also clockwise, RB into 5, so which is equal to 0. So the RB, this RB is equal to minus 2. RB equal to minus 2. That means equal to 2 is downward reaction. I took RB upwards, so that means it is downward. That's basically meaning, right? Now I also want to see RC. So we know total summation of vertical forces equal to 0. That means your RB plus RC, right? And which is RB and RC plus this 1 equal to 0, not downward, right? So RB is minus 2 plus RC plus 1 is equal to 0. So that means RC equal to 1. RC equal to 1. So simply, now if you take in the ILD diagram, right, let us say you take each span separately. For this span, you take a section X from the point C, and this span again you take section X from the C only. For both spans, you start taking section from the point C. That becomes very easy. So now what will be, because this changing, that's because the unit load moving and this, so when the unit load is between BC is different, and when unit load is in span AB, the movement changes. So in this case, what we have to do, we get a movement at XX, that could be here or this could be here, right? So either here or here. So I'll say X. This is also X section for each of the different spans. So what I have to do? So if now what I am doing for a movement at X, so I am going towards the left. Here I am going towards left, LHS. So LHS, the clockwise is negative and anti-clockwise is positive. Again, we need to remember this. So how much is the movement at section X due to RC? This into this. This is the anti-clockwise, so positive, which is RC how much? 1. So 1 into X is a X. This is as far as BC span is concerned. But now if the span AB, then what happens? If is span AB, then I have RB, which is downward, right? The RB value is your minus 2. That means your reaction is downward, right? Downward, which is 2. Downward is 2. So 2 into total, this distance is how much? This is 5. So 5 minus X, or X, or sorry, this total X minus 5. So what I want, this into this distance. So, and this it is clockwise. The clockwise is negative. So minus 2 into X minus 5. So in this section, because for this section anyway RC into X is over. For this portion, RB into this distance, RB into this distance. So this distance is nothing but total distance X minus this distance 5, because this is a 5 meter. So total minus 5 give me this, right? So this is X minus 5, and this is clockwise negative. So this becomes a total moment at the both section. So now what I do, mx means ei d square y by dx square is equal to x and minus 2 of x minus 5. Now integrating, I get ei dy by dx is equal to x square by 2 plus c1, one constant, either you can add the first term or the second term, doesn't matter. This will be minus 2 times x minus 5 whole square by 2. Right? Now integrating one more time, integrating this equation one more time. So what I get integrating one more time is ei y, which is equal to x cube by 6 plus c1x plus c2, and for the next span AB, which is minus x minus 5 cube by 3. Now applying the boundary conditions, very important, we can get the C1, C2. That means at x equal to 0, so I have a deflection equal to 0. Substituting x equal to 0 and y 0, I get C2 directly 0. Take at the first span, I mean from the x c side. Then at x equal to 5 meter, take this term only. Then y equal to 0 at the support B. Then C2 0, x is equal to 5, so I get y 0. So I get C1 equal to minus 25 by 6. Now finally I am getting equation which is ei into y is equal to x cube by 6 plus c1, which is minus 25 by 6, x plus c2, which is 0, and this is for the first span from the end side, and minus x minus 5 whole cube by 3. Now simply the ordinate, the y xa for the span AB, which is nothing but 1 by ei x cube by 6 minus 25 by 6x, and for the next span we'll have a minus x minus 5 whole cube by 3. So now see, at x equal to 10 meter, that means from here x equal to 10 meter means at the support A. So this is the total deflection, which is, we call it as YAA. So which is YAA. So substituting in this x equal to 10 here, so y I'll get 83.33 by EI. So then directly the ILD ordinate for RA will be equal to y xa by YAA. So nothing but this EI get cancelled, x cube by 6 minus 25 by 6x minus x minus 5 whole cube by 3 whole divided by 83.33. Now I can draw ILD diagram, very simple, but the one care we need to take, that whenever you are taking x up to 5, substitute only in this. If x is beyond 5 meter, so you take both terms. Whenever x is up to 5 meter, you take only first term. When x exceeds beyond 5, 6, 7 up to 10 meter, you take both terms. So this is what important. So then we can draw ILD by substituting x equal to 0. Okay. By substituting x equal to 0, so we start here. This is a point A, this is a point, let us say it's B, this is a point C. So I'm looking for ILD for RA, so I can draw ILD something like this. So this is a unit. So this is you can find out the ordinate by taking x values. You will be able to verify. This is ILD for RA. If you substitute x is equal to 0, so I should take only the first term. X is equal to 0 means this 0, so I have ordinate 0 here. When x is equal to 5, x is equal to 5, so this will be 0 and this also will have a 0. So here 0. So in x is equal to 10, I should take both terms and get an ordinate of a 1. So this is ILD for RA in a continuous beam. Thank you.